dramatically smaller, and it's very easy to study. For example, if you project to the lowest Landau level, you don't have any kinetic energy, and all you're left with is particles. Okay, I have no idea.
Chunli, quick question, please.
Yes.
So why does the Coulomb energy depends on the magnetic length?
Yes. So usually the Coulomb Hamiltonian is epsilon r, where r is the distance. And in a quantum Hall system, if you try to compute the matrix elements between some two particle states, you get some order of one, some numbers times the scale.
Maybe you can use another because that color is completely invisible.
Okay.
This light.
Oh wow, it is truly invisible. Okay, so is this better? No.
Yes. Yes.
Oh, okay. So in quantum Hall system, you try to compute a matrix elements of your Coulomb operator, repulsion operator. Then you'll get some order of one number times E squared divided by epsilon LB. Okay. LB is the magnetic length. It's for example, in the Landau-Level problem, we know the wave functions in space is has this Gaussian form, right? LB basically tells you the spread of the wave function. It's just something you solve for Schrödinger equations in a magnetic field. Okay. Okay, good. So, right. So this is just the usual quantum Hall effect. And the point I want to bring up in this slide is that whenever we can do Landau-level projections, things become simpler. Okay. Okay, now let's talk about graphene. Graphene is this semi-metal where the two bands touch at a given point known as Dirac point, and it's dispersed linearly. Okay, if you solve this sort of Dirac equation in a magnetic field, you'll find this is a spectrum. It has no the kinetic energy has no mass dependence because it's massless equations, but it has a Fermi velocity dependence. Okay. And the important point is that now at each guiding centers and Landau level and an X, your system has an octet pseudospin degree of freedom, where the octet pseudospin comes from the real electron spin, the valley. In graphene, there are the two low energy. There are two Dirac points at opposite Brillouin zone corner, and that's known as the valley. And psi is basically the particle index. It's basically reflecting the sublattice degrees of freedom. Okay, so this is a challenge, and the second challenge is that Landau-level mixing cannot be suppressed by strong magnetic field. Okay, and the reason is because the following: you take the Coulomb energy again, which is the same scale, E squared divided by epsilon LB, divide by the cyclotron energy. But now the cyclotron energy is also proportional to inverse magnetic length. So the LB cancel out, and you are left with this constant. And this is basically graphene's fine structure constant. And this thing is independent of the magnetic field. The only thing that can change this is your substrate, epsilon. Okay. So in suspended graphene, this is 2.2. It's not a small number. Okay? What it means is that as a result, you cannot do Landau-level projections very confidently. You can still do it, but there's no guarantee that this will work. Okay. Mm-hmm. And I will discuss the importance of accounting for Landau-level mixing later. Okay. So this is a very interesting phenomena in relativistic dispersion systems. You basically cannot suppress how strong Landau-Level mixed with magnetic field. Okay, so with this new challenge in mind, you can ask the questions. What is the ground state at half filling? Half filling, we use nu equal to 0, meaning you fill all the Landau levels. In graphene, you have two sublattice per unit cell. Half filling means you fill up one sublattice, 1 electron per unit cell. Okay, and we ask what is the ground state at neutrality in terms of Landau levels. Basically, you ask you have 4-fold degenerate Landau levels n equal to 0. What is the ground state when you only fill 2 out of 4? Okay, so this has a very long history before I practiced physics, and somehow the consensus that emerged is this phase diagram known as the Caritonal phase diagram. Okay, the Caritonal phase diagram is plotted in 2-dimensional space. The x-axis U-perp, what it calls, is an inter-valley scattering process. So U-perp describes a scattering process where electrons in opposite valley, K and K prime, scatter and change the valley. So this is called U-perp. It uses a single parameter to characterize the strength of this process happening. Okay. The y-axis is UZ. It's basically the valley antisymmetric channel. You take the scattering amplitude, where they remain the same valley, subtract the amplitude where K prime goes to K prime. Okay. So this is so this is the two-dimensional parameter space, and he worked it out that if your system has both positive U-perp and UZ, you should be at a ferromagnet. If U-perp is negative, it could be calculated, distorted, or antiferromagnet, or maybe charge density if both of them are negative in this quadrant. Okay, so that was sort of consensus and the guiding principle to study sort of a phase diagram in graphene. Okay, and this is just a sketch in an antiferromagnet. You have electrons equally occupy both sublattice, and the spin projection is anti-aligned with each other. In the absence of a magnetic field, the spin quantization axis can be anywhere. And calculated distortion is basically forming a spin singlet at the bond of graphene. Okay, as shown here. So good. Just one more thing. The typical energy scale associated with this parameter is very small. It's 0.1 to 1 MeV. Compared to this Coulomb scale, is roughly Coulomb scale can be 20 to 60 MeVs, depending on the field and the epsilon. Okay. Good. So that was the theory, the background. Let me tell you the experimental landscape. It all started roughly in 2014, a decade ago, where Andrea, when he was still a postdoc in MIT, he took up the challenge and measured transport experiment in nu equal to 0 graphene under a tilted field. And what he found is there's a continuous, so in this experiment, he take a graphene, and then he has out-of-plane field, and then he gradually increased the in-plane field. And he tried to see what happened to the transport measurements. And what he found is this. He found that at nu equal to 0, if you keep on increasing the total magnetic field while keeping the external out-of-plane field fixed, therefore you're increasing the in-plane field, the conductance, two-terminal conductance tend to increase, okay? But it's just a little bit shy of 2e squared over h, but it keeps on increasing. This is what he found, okay? And this can say something about the nature of the ground state, but not definitely, okay? But this is what he found. In terms of theoretical interpretations, what people believe is, okay, you could, because we know in theory, only the ferromagnetic state has some edge conductance. And the fact he sees the edge conductance increasing with in-plane magnetic field suggests the final state has to have some form of ferromagnetic order. Okay, so, and back then, Andrea thought, okay, maybe we are somewhere in the anti-ferromagnetic phase, if you increase the magnetic field, the system is gradually traversing this interaction parameter space and approach the 0 point. Okay, and as a result, the system becomes a ferromagnet and it has some edge conductions. So that was a consensus. But that was not very convincing because even if you start off with a calculated distorted state, okay, eventually, if you apply strong enough magnetic field, the ferromagnetic state is going to come down in energy and become the ground state as well. So you can also see a two-terminal increase in two-terminal conductance. So I think by now it is more or less accepted that this conclusion cannot definitely tell us whether the state is a CAF or KD state. It can only tell us that if you apply in-plane field, the system will eventually become a ferromagnet, and the ferromagnet has some H conductance. So that was 2014. Okay. Then a couple of years ago, this is from Andra's lab again. What they did is they did this non-local magnon transport experiment. So in this experiment, they cook up this very cool device. In this device, let me see. So here, so this is a biased edge states. Okay. Yeah. So the idea is that they can electrically generate magnon they can create some edge states that have opposite spin polarization, and they can electrically generate magnons to tunnel through the nu equal to 0 state to see whether the nu equal to 0 state is a magnon conductor or magnon insulator. Okay. And this is what they found. Okay.
These regions where you have edge states, how are they?
Yes.
So is it by doping or how you make it?
Yeah. Sorry, I didn't explain it very well. So this is the device, and most of the sample is nu equal to 0, so they're neutral. Mm-hmm. And this different color regions represent of different dopings. Okay. For example, if this is the red color, the pink color here should be nu equals to 1. Mm-hmm. Between nu equals to 1 and equal to 0, you should have an edge states. Mm-hmm. And the edge states we know is majority spin. Okay. Mm-hmm. If this is nu equals to 2, the edge states between nu equals to 2 and nu equals to 1 is minority spin. If you can control the chemical potential independently between these two edge states, they can scatter. Mm-hmm. And once the chemical potential is above the Zeeman energy gap, mm-hmm. they can overcome the energy to create a magnon, mm-hmm. and then you can see some signal. Mm-hmm. So that was the idea. Mm-hmm. And this is what they found. The x-axis is BPUB, the perpendicular magnetic field. The y-axis is a bias. It's basically a bias to create between this majority and minority spin edge states. Okay. Mm-hmm. And the color scale is the non-local resistance that they detect here. Okay. Basically, the only way that some signal that can propagate from here to here must go through the bulk. And the bulk is an electrical insulator because it's nu equal to 0, but it could be a magnon conductor. So that was the idea. Mm-hmm. And this is what they see. Below some magnetic field, they do not see any signal, but above some magnetic field, they see some signal. And the most important thing is the signal lies exactly at 1 and minus 1, okay? 1 and minus 1 is normalized to the Zeeman energy. Okay, so this is a very, very strong indications. The moment your chemical potential, the spin chemical potential here is greater than Zeeman energy, which is the energy required to create a magnon in the bulk, you see some signal. Okay, so this is like a hint that you must be launching some sort of collective spin excitations in nu equal to 0. And the kind of states that have collective spin excitation nu equal to 0 is naturally a canta-antiferromagnet. Okay. So this is good. And well, let me see how much time I have. Oh, yeah. We have a magnon. We have a theory to understand to to explain how to understand magnon transport in this junction, and is described in this paper. But let me just describe it very, very briefly. So the way to understand this is very, very simple. It's just like very simple optics. Okay. You want to think of this as nu equal to 1. This is nu equals to 0. And nu equal to 0, you have a magnon. And this you have two branches of magnon. One is a antiferromagnet, so it's gapless. And then nu equals to 1, you have a magnon, which is gap at the Zeeman energy, 1 here. Okay. So now, if you want to see what's the transmission amplitude, you can use conservation laws that we learned in school, right? So first, you want the energy to be conserved. So omega s, which is the spin wave, must be equal to, let's say, omega 1, this branch, okay? And Qy must also be conserved because you are scattering on a cylinder in the Landau gauge. So, but in order to satisfy these two conditions, you cannot always solve the condition, and at some point you get a perfect reflections. Okay, and this is what is being shown here. If your incident angle is too big, okay, then you basically have no magnon transmissions across the surface. Okay. You can read more about that here, but it's an interesting side project. But this is just to tell you that their interpretation of magnon transmission is more or less correct. Good. So now let's move on to some experimental activities developed very recently in the last 2 years. So basically, Ali Astani's group and also Benjamin Sasepi's group, they realized they're brave enough to take their STM tips and tunnel into an insulator. Usually, if you try to tunnel things in an insulator, you don't hope to see anything because it's an insulator. But this is a very weird form of insulator. It's a quantum Hall insulator. Although you are not supposed to have any states in between the Landau levels, but the fact is the bulk has some sigma xy, and you can still take away the electrons. Okay, I still haven't understand how do electrons really escape once you put tunnel into a quantum Hall bulk, but the fact is people, experimentalists, they have already done this. Okay, and this is what they see. So they have a graphene, they are exposed to vacuum, they can use STM to probe the atomic scale order. Okay, and this is some of the structure from Benjamin Sasepi's group, and what they see is they see some sort of a calculate order. Okay, they can tune the energy so that it's very close to the Dirac point, and they see most of the electrons live on the bond. Okay, this is as clear as day, right? This is directly showing you it as a calculate order. Okay, and likewise, this is the Princeton group data. They see that the original lattice, the original graphene translation symmetry is not being respected, and you have some calculate order forming. Okay, so this was a bit it challenges the previous transport experiment data and promise to ask the question. So what the heck is really going on in nu equal to 0 ground state? Is it a calculate order or is it a Cantor antiferromagnetic order? Okay. And this is our answer to the question. So this is a phase diagram, a gravitational phase diagram that we obtained from perturbative analysis, and I will describe more in detail later. The main result is that if you account for Landau-level mixing, it drives the transition from antiferromagnetic state to calculate distortion state. Okay. What it means is that this is kappa, which is the graphene's fine structure constant. Let me remind you, in transport experiment, in order to keep the sample clean, they usually have double encapsulated sample. So epsilon is big in transport experiments. Okay. In STM experiments, you have to tunnel electrons in. So you always have an open phase sample. So epsilon is smaller, kappa is bigger. Okay. So I want to think about what's happening to the phase diagram as I increase kappa. Okay, and what I found is, according to perturbation theory, as kappa increases, the system moves from sort of a antiferromagnetic state and then eventually become a calculated distortion phase. Okay, so this sort of provide a very simple explanation to the experiment. It's not that they are seeing different phases, but the reason is because they have very different screening environments. Okay, so this is perturbative analysis in terms of kappa. And later on in this longer paper, we did a non-perturbative analysis. We first do a renormalization group study to account for a lot of states that we cannot account for if they are Landau levels. And then at certain cutoff, we stopped and we do a self-consistent Hartree-Fock calculations. Okay, and this is the diagram that we have. Here we are plotting in terms of variables that experimentally like the external field and kappa, and you see that indeed the system changed from CAF, Cantor antiferromagnet, to Cantor calculated distortion state. Okay, if you go in these directions along the x-axis, the Landau-Level mixing is stronger. Okay, if you decrease the magnetic field, the Landau-Level mixing is also stronger. So if you go in this direction, Landau-Level mixing favor calculated distortion state. Okay.
What is the difference between the two? What
yes.
is the delta?
Thank you. This is a scenario where you do not have a boron nitride substrate potential. So in the experiment, sometimes they introduce a boron nitride.
Of the inversion symmetry.
Yeah. So that's the difference. Yeah. So
this is enough to, because in the left-hand side, you have like calculated, but in this, you have canted calculated, which is what? It's different, right?
Yeah, very good point. So, index, they belong to the same sort of order parameter class in the sense that the calculate just means your order parameter lives on the XY plane. It's like an XY magnet in the KK prime space. But calculate just means you sort of explore also the polar direction. You have a little bit of sublattice polarization. So it's not really it's not all the electrons are not equal superposition of A and living on the bond, but they could be slightly tilted towards one of the sublattice. Because in this system, the valley and sublattice is locked.
Yes.
Yeah. Okay, so yes.
So with this prediction in the STM experiments, would it be possible to drive the Cantor antiferromagnet state with a magnetic field to see a transition from Kekule to Cantor antiferromagnet by going up in the phase?
Yeah. So they, I've been talking to Ali. Yeah, they just have to crank up the field to 20 Tesla. And it's very difficult for them. But it is one of the predictions that you could go up. And the other difficulties is that, they always have DM potential. So it's very, very hard to see what is intrinsic. Yeah. But I think the underlying, phenomena is that the coupling constants, as I will describe later, strongly depends on what your kappa knot is. And if you have different experiments, you have to be careful to compare with each other because the screening environment is very different.
Maybe connected to that. So what controls this boundary, the minimum of the magnetic field that you need to drive the transition from the CKD to the quantitative?
Yeah.
What controls that value? Is it the?
It's very tough. It depends on many. We try to do almost like a first principle calculations. I can say something. I can point out to some coupling constants. That's relevant to driving this in the perturbation theory. Okay, but in these calculations, it's a lot of things going on. But I can address your question later. Okay, but these are nothing along this line is universal. Okay, and this two black dash line is the kappa knot for transport experiment, and this is for STM experiments. In STM experiments, I wouldn't bet on this number, but they have to go up to maybe like 30-something Tesla to see it. Okay. Yeah. I mean, it's a very, very Yeah, there's some technical issues in this calculation that is, usually if your calculation is good, it shouldn't depend on where you do a transition from RG to self-consistent Hartree-Fock. But in this calculations, because it's still running as log, it depends a little bit on where you choose your because we first do an RG and do a self-consistent Hartree-Fock later. And if it's a good calculation, it shouldn't matter where you transit when you switch from one method to the other.
Yeah.
But we do have some dependence here that we do not know how to get rid of. Okay. Yes.
So if you got B for the weak magnetic field around 4 Tesla and with the Landau-Level mixing around 0.2, what is the phase here for the Y direction?
Yeah. Somehow my student decided to leave it white to indicate this is like a sublattice polarized state. But it's really like this and CKD, they're really not different from each other in terms of order parameter class. This is like if you're here, basically all the electrons are polarized and given sublattice. And the reason is because you have a BM potential.
It is like charge density wave.
Exactly. You can call it a charge density wave, but it's not induced by interactions. It's just like you have a potential because you put a BN, boron nitride, the boron and nitride have different potential. So you have AA and AB, the potential is different. So naturally, the electrons want to go to one of the sites, AA, for example. It's not induced by interactions. You can call it sublattice polarized state, but I will refrain to call it from a charge density wave. You can call it that way, but some people do, but I don't think it's good. Yeah. Okay, good. So let me tell you how I got all these results, right? Looks like I'm just pulling out from thin air. So the way I'm going to do it is in 3 steps. First, I will try to advocate the standard model of graphene, which I think everyone in the community should probably think about this line, start to use a standard model of graphene to model physics. And we can estimate the back coupling constants in the standard model, and we can do a RG on these coupling constants. Okay. So this is graphene standard model. It's not invented by me. It's invented by Lionel, Kazif, and where's his name? But it's a very important paper in 2007. Please look it up. It's very good. It's very hard to understand. Okay, but I will explain it to you. So the model consists of 3 terms.
Malco is one of the authors.
No, Lionel, Kazif, Teflik, Alexei Teflik.
Okay.
Yeah. Okay. Yeah. Okay. So it has 3 terms. First, you have a kinetic energy for the non-relative relativistic electrons, the standard term. You have a bunch of long-range Coulomb interactions. Okay, and then you have a bunch of H of A. A stands for antisymmetric term. Antisymmetric in what? Antisymmetric in both the valley and sublattice. Okay, because on the lattice scale, the system really doesn't have a continuous rotation symmetry. Okay, and so there's no reason why the interactions must be density-like interactions. Obviously, this must be the strongest scale of the problem because this is coming from classical electrostatic problem. But this, and especially in dilute limit, it should dominate. But this should also be present. Okay, and this term, although you try to estimate this, as I will do later, turns out to be a very small number. Under renormalization group flow, it can become very, very big. Okay, so this is the standard model. Unlike standard model, it's simpler than a standard model that we have in high energy physics. It only has like 8 parameters. Okay. Good. So let me tell you how we can estimate those back coupling constants. This G here. Okay. Well, to do that, you need some 3-dimension. You need to solve a Schrödinger equations in 3 dimensions. Okay. And what we do is that we assume that the block wave function is a linear combination of atomic 3D atomic pz orbitals. So these are pz orbitals, two pz orbitals, and we take a linear combinations of them to get our block wave functions. Okay, we need a starting point. It's not like a DFT calculations. I know there are many DFT experts here. If you can do a DFT calculation to get these numbers more precisely, that would be great. Okay. And let me give you an example how to compute this. If you want to compute G per equal to 0, one of the coupling constants, you basically just have to compute this overlap charge. So this overlap charge is between opposite value. Okay, so we want to take this expression at Ka and Hermitian conjugate K prime A, and evaluate this R2, R1, and compute this 6-dimensional integral. Okay. However, this thing looks sort of trivial, but there's some detail that's important when you evaluate this. For example, the most important thing is that this thing is 1 over R, so it decays very, very slowly. You shouldn't do it in real space, and you should do it in reciprocal space like this. Okay, if you do reciprocal space, the thing converge. Okay, and you will give you some number. And this is described in detail how to compute these integrals correctly in this paper. And the reason why I spent some time to point out this is because the previous estimations that did in real space lead to incorrect results. They basically found a negative sign, but you can prove almost by inspection that this has to be positive definite. And the reason is because if you try to compute this thing in real space, the Coulomb integral does not converge. Okay, we have communicated to the authors of this paper, and they did not, object to our suggestions. Okay. So this is the our result. We have estimated those bare coupling constants. You can see hundreds of MeVs per nanometer square times nanometer square. And the most important thing is that this guy, GZ perp and G perp Z, the one that you change sublattice, okay? Whenever you change sublattice, the optical phonon can come in. And optical phonon always contribute to attractive interactions. And in our estimation, the optical phonon wins the bare electronic contributions. And as a result, it gives you attractive interactions whenever you enter sublattice, okay? And then you have this too, which is sublattice and antisymmetric and some intervalley channel, okay? Good. So these are the starting point. This is the estimate for the coupling constants of the standard model in graphene. Okay. Now, in the 0th Landau-Level projection limit, I can recover the caritonal phase diagram. In the 0th Landau-Level, if I project this coupling constant to the 0th Landau-Level, this guy, the intersublattice valley antisymmetric vanished because in 0th Landau-Level, the valley and sublattice is locked. Intersublattice, if you flip sublattice, you don't flip the valley, then it's 0. Okay. Likewise, if you do intervalley, the sublattice symmetric is 0. The only term that's not 0 is when you have sublattice antisymmetric, valley antisymmetric, so you don't flip anything, or you flip both the valley and sublattice. Then you can survive 0 Landau-Level projections. So if you project this, then the system is somewhere here, sitting at this point, which is an antiferromagnetic phase. Okay. So now let me crank up, let me now include Landau-Level mixings. Okay. To compute Landau-Level mixing, we use a perturbation theory. It's very simple. You have a projection.
So,
yes.
Actually, before you go into that, so in order to estimate the electron phonon coupling contribution, you use only the lowest optical phonon? Or
there are 6 phonon branches, but the strongest electron phonon coupling come from the highest optical phonon branch. So people have estimated the electron phonon coupling constant with all these phonon branch, and the highest one is with the highest optical phonon branch. So I only use that branch, and that branch happens to be
So it's only, you use only that one, not the others.
No, yeah.
And so the energy difference does not compensate for the change in the.
Say that again.
Because I guess that even if the lowest ones have smaller coupling constant, they have lower energy. So if you think perturbatively, they should also contribute. Right?
Yeah. So you are talking about the phonon gap, right? So
yes.
So I don't remember the details, but the conclusion I think is that this was done way before us, right? The conclusion is that if it's sufficient to account just for the highest optical phonon branch, because for example, the acoustic phonon branch, they just get mixed into the long range Coulomb, right? Because they are just changing of Fermi velocity. They're not important. But it is those that go up to that has inter-sublattice scattering that's important. Yeah. Okay, so Landau-Level mixing, you do perturbation theory. P here is a projection to the zeroth Landau level. P perp is the complement of these projections. And this is your energy denominator. And we put one S and one A. Okay? S is a symmetric. A is antisymmetric. Okay? So this diagram, this term has an order, you can count the scale. Okay? So HS has dimension, HS has a scale of E squared epsilon LB. Okay? The energy denominator has H bar, VF, LB, and HA is roughly a G. Okay, so this thing will give you the LB cancels out, and you give you roughly G times kappa, your fine structural constant. Okay, so this is the order I'm evaluating. Okay, I'm evaluating a contribution to leading order in kappa. Okay, times G. Okay, I did that. Okay. So, and these are the diagrams that I have. Okay, if you just do this thing with accounting for many body physics, you get 6 class of diagrams. And so what this means is that you have 2 lines. One line is a long range Coulomb, the other line is a delta function. Okay, and you want to insert them in all possible directions. Okay, so what do I learn from these calculations? First, I can ask, does delta function remain short range after mixing one of R? It's non-trivial question, right? You try to let 2 electrons, you let them interact only when they come together, and you let them propagate, and then let them interact when they're far away with one of R. So there's a question, does delta function remain short range after mixing with one of R? And surprisingly, we found the answer is yes. Okay, and I'll tell you why later. And the second thing is there a process, is there a single diagram that's responsible for driving antiferromagnetic state to KD transition? And the answer is God is very kind to us. Normally, a Feynman diagram, you cannot pinpoint which diagram gives you that. Everything is mixed up. But in this case, there's one single diagram, which is called a double exchange diagram, that is solely responsible for this transition. Okay, the other I'll just cancel out. So I'll mainly focus on this guy later. Okay. So in order to measure the distance inside the magnetic field, okay, we need to choose a basis, because I tell you it's remain short range. But how do I measure? How do I measure the range? Okay. One way to do it is to use the Haldane pseudopotential. Okay. So okay. So do any of you need me to remind you Haldane pseudopotentials? Okay, good. So if you have 2 electrons interacting in a magnetic field, okay, usually in classical let's say you have one electron, and the quantum numbers is N1 and M1. And N1 is the Landau level of the first electron. M1 is the guiding center or the angular momentum in the symmetric cage. So if you have two particles, the Hilbert space is just a direct sum. Okay, M1, M1, N2, M2. Okay, and you can work out the algebra. It turns out that in this two electron problem, the center of mass coordinate and the relative coordinate commute with each other. Okay, that's not a trivial statement because in a magnetic field, you know, the guiding centers do not commute with each other, Rx and Ry, but in their center of mass and relative coordinate turns out to commute with each other. Therefore, you can use a set of guiding centers, a set of Landau-Level index and guiding center for the center of mass, and a small m and little m for the relative. And then here you just have some coefficients that to go from these two bases. Okay. Now the good thing about this basis, this is easy to write down, but we really want to work with this basis. Okay, because if you work with this basis, we know that if you have any two particle interactions, that is independent, that only depends on the relative position on the distance, then the matrix element become very, very simple. Then you have delta n prime is independent of the center of mass. Okay, and you only have V and M prime, and then you have a angular momentum conservations. Okay, I think it's n minus m, sorry. This is angular momentum conservations. So you can characterize your full Coulomb Hamiltonian with just three integers, n, m, n prime, and the last one is given by this. Okay, so this is the power of potential to potential. You can characterize the range of your full two-body interactions with just three integers. Okay, and this is the basis we want to use. So this is just the way I write the basis. If you project n and if you are in the lowest Landau level, then this is 0. This is 0. This is also 0. Then you are left with, if this is 0, 0, m has to be equal to m prime. So you can characterize your potential with just a single integer n. Okay. So, and you see, that's why you see in a lot of numerical studies, you just have to, a fractional quantum Hall effect, you just have to provide a list of numbers, how the V decay with n. And you characterize the full potential in the zero Landau level. Okay, so I'm going to do the same thing here. It turns out that the sublattice asymmetric part also have this dependence. You can also characterize it with potential potentials. Okay, and this diagram turns out to vanish. This diagram vanished because the propagator, this bubble in the middle, is independent of valley. The G is independent of valley, but this is valley dependent interactions. Therefore, this is 0. Okay, and because this diagram is 0, it does not introduce long range Coulomb interactions. Okay, this is the main diagram that can physically generate long range interactions, but this vanished because it doesn't have valley dependent structure. The other diagrams all involve certain amount of exchange interactions which require electrons to come close. So, and we have estimated that the m equal to 0 channel and m equal to 1 channel, the ratio is roughly 20. Okay, in other words, the system remains short range even after you do Landau-Level projections. Okay. This is good because then they can stay within the realm of this two parameter space. We don't have to include all the other coupling constants that is being generated. Okay. This is too much detail. Now I realize. Okay. But let me just point out we have, I find this very interesting. There's a new way to generate attractive interactions coming from purely repulsive interactions. And the way to generate attractive interactions is evaluating the matrix elements of this diagram. So I will just go through it briefly. Okay. So in this diagram, here you have a long-range Coulomb interaction potential. So 2 pi e square of q. And here you have a delta function interactions. Okay. And in the middle, you have some virtual particle, n5 and 6, psi5, psi6 could be particle and whole index. Okay. Now, if you try to compute the matrix element of this diagram, this guy gives you G per perp, and then you have some matrix elements here. Okay. And the matrix elements XX stand for tau X and sigma X. Tau X, sigma X are just the valley and sublattice. And you can evaluate this thing in this vertex. The thing that leaves the vertex is psi5 n5. So I put a psi5 n5 here. And this thing leaves the vertex is 0 bar. I put a 0 bar here. The thing that comes into the vertex is 0 bar. So I put a 0 bar here. And then the thing that comes into this vertex is psi6 n6. Okay. So these are the in state of the vertex. These are the out state of the vertex. And I put the matrix elements in between, the scattering operators. And you can evaluate this quantity because these are electron and holes diagrams, psi5 and psi6 must be 0. Okay. And as a result, you can purely based on matrix elements effect, you get an attractive interactions by combining 2 repulsive interactions. Okay. So this is very, very cool. Okay, it doesn't happen in the original quantum Latinger analysis. It's strictly speaking a relativistic electron phenomena. Let me skip this. How much time do I have? -5, I guess. Okay. Let me just maybe end the suffering for everyone and give you the main message. Okay. So the main message is that the remote Landau level strongly enhance the strength of the coupling constants. So you have to account for them. And we found a new mechanism to generate attractive interactions by combining Coulomb interactions with intervalley repulsive interactions. And the potential potential in m equal to 0 channel strongly dominates the m equals to 1 and 2. So this actually validates Kharitonof's 2-parameter phase diagram. Okay. With that, I thank you for your attention.
That came to an abrupt end, but I think
very quick question. So attractive meant negatives going left in the Kharitonov phase diagram, or
Yes.
so towards the Kekulé?
Yes. And this is the diagram that's responsible for the transitions.
Yeah. We have more time for questions.
Yeah.
Anybody want to ask me? Is there any more kind of physical understanding of why this turns out to be negative? It's kind of like, it has to do with the fact that it's an exchange, double exchange diagram, or?
Yeah, it has to do with first psi5 and psi6 has to be negative. So they have to be particle hole diagrams. So these are my bases. My basis psi +1 is electron Landau level, psi equal to -1 is whole Landau levels. If you're doing this type of diagram, psi5 and psi6 have to be negative. Has to be the product of psi5 and psi6 is negative. They have to have relative minus sign. And if you try to compute, because the matrix elements here, we know is positive. Okay. Okay, this is just long range Coulomb.
Mhm.
But if you compute the matrix elements here, you will find that it's sort of right. So you have to compute this form factors,
Mhm.
and it turns out that it comes out proportional to psi 5 times psi 6,
Mhm.
and
So it has to do with the fact that it involves an intermediate state which has a particle hole
yeah,
excitation
yes.
in different Landau levels.
Mhm. Yeah, I don't have a ball and stick model to explain why this turns out to be attractive, but it's good to think about that, I think.
Sometimes people in 2 dimensions many years ago used to talk about the fact that you could get attraction from over screening, right?
Yeah. But this is a purely matrix elements effect coming from.
Yeah, but so
Right.
the intermediate state is kind of like trying to screen this interaction.
Yeah, so yeah, this is distinct from what Colin Lattinger did. In the sense, if you just do 2-dimensional electron gas model, or just electron gas model without any structure in the wave functions, you never get this matrix elements effect. And this diagram, in fact, will give you, if you just repeat this diagram, as many of you might know, but it just gives you a repulsion in singlet channel, right? This is the paramagnon model. If you approach, ferromagnetic critical point, then the singular repulsion become very strong. And but here it's giving you attractions.
But in that case, the vertex is the same.
They only have, you have to repeat this channel many times because you want to approach criticality.
Yeah. So the lines of interaction are the same, not different, right?
They only have long range Coulomb, right? Yeah.
All right. Yeah.
Just one more? So, in the experiment with magnon transmission, you assume that the only nu equals 0 state that has collective modes is the quantum ferromagnet with magnon. But what about the Kekulé state having collective modes too? That would also cause some.
Yeah, that's a very, very good question. So there are a few hints at let me answer your question with experimental data first. So
Well, the Zeeman scale.
the first thing is the Zeeman scale. So that's a very, very strong hint that why does suddenly things turn on a Zeeman scale, right? If you have some collective modes in the KD state, then they have to go by fine-tuning to reach certain degree such that it's fine-tuning of the gap of the collective mode so that it's at the Zeeman scale. And that's number one. And number two, we kind of know what this state and this state is. This is a majority spin, minority spin.
Yeah.
So just by quantum number conservations, we expect this guy to carry spin quantum number. Yeah.
Good. Thanks.
Okay. Yeah.
So you said this attractive interaction is a relativistic phenomenon. Does it mean that if you had a mass term in the Hamiltonian, this would change or not?
So I would say no, it wouldn't change, and the reason is because it's because of things I didn't discuss. It turns out most of the contribution from this diagram does not come from Landau level that's close to the Fermi level, that's close to neutrality. So when you apply magnetic field, you get some Landau levels, right? But in relativistic Landau level, they become more dense as you go out. Okay, the density of states keep increasing. And actually, most of the contributions from this diagram come from those states that are very, very far away. So even if you open a tiny gap here, it wouldn't affect those contributions coming here. Yeah, and this is the log dependence of the number of Landau levels that I didn't talk about, but it's very peculiar because naively if you imagine, okay, the closest Landau level should contribute more to renormalization because of energy denominator being smaller, but that's actually not correct. The reason is because if you go further out, sure, your energy denominator is increasing, but the density of states, the number of Landau levels you have as you go further also increases. And it's increasing in such a way that the number of Landau levels outweighs the energy denominator penalty, so that the remote Landau levels actually contribute. Yeah.
Well, so it's already 1 hour since we started. Maybe it's time to close the seminar here. If you have any further questions, you can talk to him privately. Okay, so let's thank Chunli for